Welcome to Nitty Gritty Talks, and today we're going to talk about nitty gritties of binary translation. This is the second video in the series, so if you are new to this series, please check out the first part where we talked about terminology and different kinds of translation and compilation, and that would allow to move on to the next part. So this is recorded in sequential order. And today we're going to discuss the trade-offs between static and dynamic translation or just-in-time translation and see which one has the benefits over another in which cases.
What are the trade-offs for static between just-in-time compilers, optimizers? Yeah, I'm going a little bit wide here, but probably that will give some insight. So what we are trying to arrive at is system level just-in-time compiler, and what is system level will be on the next slide. And looking for differences with other existing technologies to understand where the place for this technology lies. So if you take something with which you can compile and then run, so it has larger scope for looking for some code patterns and ways for optimization. So that's compile unit like a C file, or even more if we are talking about link time optimizations. And it's definitely at least a function scope, and it can be several functions. And if, for example, we have several like intertwined calls from one function to another, it's able to spot that and optimize for that in line functions. I mean, lining is just copying the body of one function into the other, eliminating thus the function call, which may speed up things. Yeah, and for a just-in-time optimizer, it's not able to do that at all. There is no possibility, like physically, to do that, even if it very wants to. So what just-in-time optimizer sees, it sees execution trace, and it's the sequence of dynamically executing instructions. So, for example, you're having quite a large loop, which is probably like 1,000 instructions, which is not very uncommon. Yeah, and with the JIT optimizer, you are seeing instruction after instruction after instruction, and it has some scope for tracking. It may be in the range of hundreds of instruction. It may be sometimes very large scope, but we need to see that it has a cost. The more you want to track, the more time during the execution you have to spend for it, and sacrificing this time for not running the actual useful code. Yeah, and so for example, we even don't see that there is a loop, and that's a limiter. We cannot optimize thus this loop, and that's of course a limiter. And the other way around, we are not paying attention which exact unit this instruction comes from. So, for example, we can have a dynamically linked library call, and we have some instructions in our applications, and then coming after that, some instruction in the dynamically linked library. And for JIT optimizer, it doesn't matter. Of course, I'm talking about like system level optimizer because for application level optimizer, this library may be not contained inside the application. So yeah, and we can see through these calls and optimize this because it's quite expensive. And maybe we can see even some operating system events happening during the execution and optimizing for those. So yeah, that's kind of both ways, but I would say that having larger scope as the compiler does would be very beneficial. And another trade-off is when we compile and run code afterwards, it's allowed to spend a lot of time on optimizing, and JIT optimizer does not have that luxury. So we have always to balance the code the time we spend during optimizing things, profiling things, doing all kinds of this stuff with actual code execution, and we don't want this to be very disbalanced. We don't want optimizing 10 seconds and execute in 1 second, but very, very efficiently, because we could just have 5-second run without any optimizations, for example. And another thing which plays to the benefit of JIT optimizer is its ability to account for dynamic behavior and adapt to it. So we discussed how compilers can approach to this, doing profiling runs and doing like second round of optimizations according to dynamic profile. But JIT optimizers can have this profile as many times as they want to and adapt thus to ever-changing behavior. So for example, GCC, you run the test bench and the real code may differ. And for a dynamic optimizing system, you have, for example, an application which runs a lot of time, and first 10 seconds it prefers to read one address, and 10 seconds after that it's having another address in the registry, for example. And we can adapt to that. So there is a large spectrum of things we can do here, but in essence, it all comes to ability to track the dynamic behavior and adapt it. And the last thing I wanted to point out is that compilers make the executable, which you can run only on a specific machine. And for JIT optimizer, you can compile like codes, and then, for example, having several front ends for dynamic optimizer, and accept several types of incoming codes. And this will not need any recompilation when you like switching machines. So front ends is just like with the regular compiler, when you have your incoming code and transform it into the middle intermediate representation. For example, you have GCC. For it, you have C front end, you have, I don't know, other language front end, Haskell front end, Fortran front end. And then you transform all of these different languages into the same intermediate representation and doing the same like scope of optimizations for those. And then having backends which are translating the intermediate representation, the optimized one, into the specific architecture you want to compile to. So that's how like compilers do a little bit of scaling in their design. So for example, if they need to support new kind of architecture, they just write a new backend, and other pieces stay the same. And the largest piece is probably what's happening in the middle, which is like doing all the optimizations, which kind of has many things to do, and you don't need to write that.
And that's it for today's video. There are just two main simple takeaways from the information from this comparison of static and JIT optimizers. So the first one is that JIT optimizer has to balance the compilation time which happens and shares the time and resources with the actual executing code. So it has to be very diligent with how much time it actually spends in the compilation. And that goes as a thread through the whole topic of dynamic translation. And another thing which plays to the benefit of the JIT translation is that it can utilize dynamic behavior. It can profile the code and see different ways in which you can adjust the code to make it faster, which is not possible with static compilation. This video is designed for people familiar with the basics of computer science, and I know that may sound a lot at some moments, so please ask any questions that you might have, and I will try to answer that. Maybe some topics need some dedicated discussions. I would be glad to hear about it, and feel free to support me, giving a like and subscribing to the channel. So stay tuned for the next video where we will discuss trade-offs between system level translation and application level translation. I'm trying to make this channel half and half of professional videos and like general topics videos. So I hope that the next video will come 2 to 4 weeks from this time. And thank you for watching today, and hope to see you next time.